Why, hello and welcome back to Lecture 8-1A, which is on grid-based mapping with a known robot pose. The summary and learning objectives for today's lecture are that occupancy grid maps are a popular approach to representing the environment of a mobile robot given known poses. In this approach, each cell is considered independently from all others. It stores the posterior probability that the corresponding area in the environment is either occupied or not. Occupancy grid maps can be learned efficiently by using a probabilistic approach, and reflection maps are an alternative representation, which we will cover in Lecture 8-1 as well. In this type of map, they store each cell the probability that a beam is either reflected by this cell or that it passes through. And finally, we will provide a sensor model for computing the likelihood of a measurement and show that the counting procedure is a good way of looking at the underlying reflection maps and the optimal map. Recall that much of the content from these lectures comes from probabilisticrobotics.org and the Probabilistic Robotics textbook written by Dieter Fox, Sebastian Thrun, and Wolfram Burgard. Please check out their website, probabilisticrobotics.org, for more great content there. And welcome, and I hope you enjoy. So the first question you may ask is, why mapping? So learning maps is one of the fundamental problems in mobile robotics. Maps allow robots to efficiently carry out their tasks, such as localization, which we previously studied. Successful robot systems rely on maps for localization, path planning, activity planning, etc. So you want to start with the simplest approach first, which is mapping with known poses, and in a grid-based map, which is what we're going to study today. Mapping as a chicken and egg problem. So far, we've learned how to estimate the pose of a vehicle given the data and the map. That was localization. Mapping, however, involves simultaneously estimating the pose of the vehicle and the map. So the general problem is therefore denoted as simultaneous localization and mapping, which will be covered during weeks 9 and 10 lectures. Throughout this section, we will describe how to calculate a map given we know the pose of the vehicle. So there are several types of SLAM problems. Here are a couple of them. When you have grid maps or scans, that's essentially where the robot is traversing the world and determining whether a certain location or cell in the world is occupied or not. So that would be a grid map. Landmark based is where you're looking for distinctive features or characteristics about the world, and you're using that in order to build the map. So you may have some information about certain features or certain beacon locations, etc. But it's more than just, are things occupied or not? So the general problem of mapping, as you can probably imagine, is once again, you have sensors, so you're going to have sensor error. You have robots moving around, so you're going to have odometry error. And then you may have a robot with 24 ultrasound measurements, but what does the world really look like? So what you see here in this image is as the robot drove around, the red lines represent the robot's sensor readings, and those small dots represent the robot's pose in the world as it was moving and collecting this data. How do you now translate this information into a map of the world? So here are some of the problems with mapping. One of them is sensor interpretation. How do you extract the relevant information from raw sensor data? Number two, how do we represent and integrate this information over time? So as the robot's moving, the position of the robot's moving, and it's collecting sensor data, those somehow have to be integrated together to create the map. And robot locations have to be estimated. We already know this is true because we look at things like accumulation of error as the robot moves around. So how can we identify whether the robot has previously visited a location or it's visiting a new area, getting new data? And this problem is called the data association problem. So the general problem of mapping is mapping involves giving sensor data. So D would be U1, Z1 to UNZN, where U1 is the motion command or the motion model, and Z1 would be the sensor model, and we have to put these together because the data involves the robot's pose, the robot sensor data, and how they have to be integrated together in order to make the map. So to calculate the most likely map, we call it M star, where our argument is to maximize the probability that this is our map given this set of data. So find the map with the maximum likelihood given all the data that we have. So here's an example of a map that was created at Victoria Park, where the map was created from a car that had a 2D laser scanner on the top of it. And it was driven around this park here in Sydney, Australia. And they were able to extract 2D features of the world by focusing on the pixels, which represent the robot's movements of data, as well as that tracking. So this is what we're going to try to accomplish today. Although it won't be a feature-based map, it will be a grid-based map. So grid maps discretize the world into cells. The grid structure is in a rigid, the grid structure is rigid. Each cell is assumed to be either occupied or free, which makes things easier because it's binary. It is a non-parametric model, and it requires a substantial amount of memory resources because it has to store all the information about the map in terms of these cells. But it does not rely on a feature detector, which is the good news. It's really just using range sensors to say there's something in this cell or something not in this cell, and then mark it either free or occupied. Here is an example of an occupancy map where, and this is the same hallway we've seen before in these lectures, where the robot drove around and it extracts data to determine whether there's a wall there or not, or there's an area that is occupied or not. So it creates a binary map of this space using the probability in a recursive based fashion to filter and approach whether a location has an occupied cell or not, where it starts out with a prior belief for every cell of 0.5. And then if the value is above 0.5, it's white, or if it's below 0.5, it's black. You can actually, that's arbitrary. You could flip it in the other way as well. But basically, probabilities that either exceed the threshold represent either occupied or free, and those below the threshold would represent either occupied or free. So assumption one is that the area that corresponds to a cell is either completely free or completely occupied. So what that would mean is that even if partial parts of a cell are occupied, we either completely cover that cell as occupied or free. So as soon as there's anything in that cell at all, we say that cell is occupied. And so here would represent the grayed out areas being occupied space and the white areas being free space. So in this representation, each cell is a binary random variable which takes on either a value of 1 or 0, represented as a posterior random belief that the cell is occupied. So P of Mi would be 1, or P of Mj would be 0, where I and j represent each of the respective cells in the map. So in the occupancy probability, each cell is a binary random variable that models occupancy. So a cell is occupied, as we just said, if P of Mi equals 1, or a cell is free if P of Mi is equal to 0. No information means that P of Mi equals 0.5. So that is the uniform prior that we give to every cell in the world at the very beginning. And for this analysis, we assume that the environment is assumed to be static. So people aren't walking around, doors aren't opening and closing, etc. So the second assumption is that the cells are each random variables and they are independent of each other. There's no dependency between the cells. And what that means is that if cell 1 is occupied, that tells you nothing about whether cell 2 is occupied or not. So they are independent of each other. And so in our representation, because of our independence assumption, we can say that the probability of a given map is now the product of the probability of each of the cells being occupied or not, where there's no dependence on each other. So there's no conditional probability here. So it's the product of the probability distributions of the individual cells. So the probability distribution of the map given by the product of these distributions can be described as following. If I have a 2 by 2 world shown here, I can represent that as a 4-dimensional vector where that represents cells 1, 2, 3, 4 with either a 1 or 0 that represents whether they're occupied or not. But that can then be broken down into each of those 4 cells or 4 independent cells with the probability of each multiplied together to get the overall probability for the map. And this concludes lecture 8-1A. I hope you've learned a lot. I hope you enjoy, and I hope you're going to come back for lecture 8-1B. Have a robotastic day.